In this video, we're going to be looking at some important ideas like sequences, nth terms, and discrete functions. This is the first lesson of Unit 6, Discrete Functions, as part of my Grade 11 Functions course. If you want me to teach you this entire course, visit my website, tutor.ca, and enroll in the Second Teacher program, which includes video lessons, private tutoring, notes, and practice problems for every section in Grade 11 Functions. I hope you enjoy the video. Hello everyone, I hope you're doing well. Welcome to Lesson 30 in the Second Teacher Programs course on Grade 11 Functions. Here we're taking a look at similar content to Section 6.1 from the textbook, which is sequences as functions. So we are beginning our Chapter 6, which is the study of discrete functions, which is just a special kind of function, which we're going to define in this lesson. And so we're going to start by looking at sequences and how they're going to be related to functions. And so it turns out that sequences like we're going to define in a second, but you probably know sequences of like 2, 4, 6, 8, things like that can actually be thought of as a function. And so this entire chapter is all about studying functions like that and how they can be used to use different real world situations, and also how to advance math in certain positions. Okay, so to begin, let's just remind ourselves what a sequence is. So I'll take up the definition from the notes here quickly. So the definition of a sequence is it is a list of numbers separated by commas which begin at some number. Importantly, they begin at some number and may or may not end. Okay, usually there's some rule to get from term to term, like add 2 each time. So for example, I just go through some examples here quickly, right? So if I have the sequence 2, 6, 10, 14, 18, ... So that is a sequence because it's a list of numbers separated by commas which begin at some number, okay, and may or may not end. So this doesn't end, right? This ... you can read as so on and so forth. Just sort of keep going as how it is, right? And usually there's some rule. It doesn't have to be a rule, but usually there's some rule to get from term to term. And so you see from here, we can say that the term, right, you add 4 to get from term to term. And each thing is called a term. Each thing inside the sequence is called a term. So we add 4 each time to get from there to there. Let's take a look at some more examples. Okay, so then just counting the numbers 1, 2, 3, 4, 5, 6, 7, ... whatever, some huge number, right? 100,000. This is a sequence. Okay, it is a sequence that does have an end, right? So it goes from 1 to 100,000, right? Or you know what? I'll just add another 0. Or another 2 zeros and make it a million. Or no, there you go. Now it's a million. And so we can, this is still a sequence because it's a list of numbers separated by a comma. Okay, and there is a rule to get from point to point. It's just add 1 each time, right? So you're literally just listing the numbers. But the rule is add 1 to get from term to term like that, right? Okay, and we're going to study kind of like different kinds of rules. So this is a type of rule. It's a type of rule called a recursive formula. And we're going to learn about that in the next section. 6.2 is about recursive formulas. But, for right now, you can kind of already understand, okay, well, it's just, it's when you have terms and you go between the terms, there's some rule you have to apply. So add 4, add 1, something like that, right? But they honestly don't have to be how this is here, right? So like how I've been doing, like, add 1 each time. Like we could have more complicated sequences like 3, 9, 27, 81, ... right? And so this would be, well, you have to multiply by 3 each time to go between the terms, right? That's the recursive formula. And so it doesn't have to be addition, subtraction, or anything like multiplication. It's just there's some rule to go between the terms, and in fact, there can just be some rule to get the term number. So what I mean by that, right, look at my notes here quickly, is let's take a look, for example, at this sequence. 5, okay, 5, 10, 17, 28, ... So let's try to see if we can identify some kind of rule to the sequence. Well, let's first think about adding. We add 5, then we add 7, okay, then we add what? We add 9 here, right? Okay, so not consistent. We're also not multiplying. You multiply by 2, and here you multiply by, well, whatever, not 2. But interestingly, you can see here, what about the differences between what you're adding? Oh, you add by 2, add by 2. So maybe the next time we're going to also add by 2. So here we're going to add by 11 to get to the next one. So 11, maybe the next thing in the sequence is going to be 39. You know, it could possibly be that. You see how I did that, right? Like we're going 5, add 5, add 7, add 9. Okay, so that number, the amount that we're adding, is going up by 2 each time. And so we can say maybe the next one we're going to add 11 to the next one, right? To get to the next term. But that's just an idea. You know, there's lots of ways you can think about this. So to try to analyze the sequence here, what we would like to do is actually label each of the terms. So I'm going to call that, I'm going to label it term 1. Okay, I'm going to label that one term 2. I'll label this one term 3. This one term 4. And this one term 5. Okay, so now we have a name for each term. Right? And so we can say, okay, well, you know, this definitely, I understand if this doesn't jump out at you, right? This is just an example, right? I'm just going to show you that there's going to be underlying things in a sequence. So term 1, right, is 5, obviously. Term 1 equals 5, okay? But that's actually also 2 to the power of 1 plus 3 times 1. Okay, not 31, 3 times 1. Where does 1 come from? The term number. Let's see if that holds true for the next one. What about term 2, right? Term 2 is, of course, 10, but is that 2 to the power of 2 plus 3 times 2? And again, how am I coming up with this? Because I wrote the example. I'm just trying to show you that there is a underlying rule to the sequence here, which is that you take the, you know, let's just check if that's true. 2 to the power of 2 is 4, plus 6, 4 plus 6 is 10. Yeah. Right? Let's just check if, let's just keep going. Let's just see if it fits for other ones as well. So term 3 is 17. Okay, and let's see, is it true that it's 2 to the power of 3 plus 3 times 3? 2 to the power of 3 is 8 plus 9. 8 plus 9 is 17. Okay, so yeah, it is working out. This does appear to be the rule. Right, term 4. Let's just do one last one. Term, I'll use color, that color. Term 4 is equal to 28, which is 2 to the power of 4 plus 3 times 4. So 2 to the power of 4 is 16. 16 plus 12 is 28. So we do get exactly the thing that we're looking for. And so you see that there's an underlying rule here that relates the term numbers, right? The term numbers to the value of the term. So when I say the value of term 5, I mean 39, right? In this particular sequence. This sequence I gave it as an example here, right? So when I say the value of term 4, I'm talking about 28. Right? When I say term 3, I mean term 3, right? The label 3. Where the value of term 3 is 17. Okay, there we go. So there is that. We can see how this relates. We showed that there is a relation between the term number and the value of the term. Okay, specifically, the relation is that the value of the term, right? Value of the term is equal to 2 to the power. You know, I'll just type this out. So the value of the term is 2 to the power of the term number, okay, plus 3 times the term number. Okay, and so we just verified that that's true here, right? For this one is that, yeah, 2 to the power of 1 plus 3 times 1 is the value of term 1, and the same for the rest of them, right? Okay, so let's just take a moment to learn a little bit of new notation. So instead of writing the word term 1, okay, let me just copy this quickly. Instead of writing the word term 1, term 2, term 3, we have a little notation for it. So I can replace term 1 with this symbol, T1. And the 1 is kind of like low. It's like an exponent, but lower, right? The bottom exponent. So it's called sub. You would pronounce, if you really want to just say this as a symbol, it's T sub 1. But you can also just call it T1. That's fine. And so then you might expect this one's going to be T2. This one's going to be T3. And it kind of stands for term 3, term 4, and all that. So T5 right, would be the next term. So t1 is equal to 5 in the sequence. T1 is equal to 5. What that means is our first term is equal to 5. T2 equals 10, and so on and so forth. Right? Okay, so let's make a little table of values for a simpler sequence, maybe a simpler one here. Right? Let's say I'm going to get a sequence, I don't know, maybe this one up here that I gave an example. 2, 6, 10, 4, 2, well, even a simpler one actually. You know what, I'll start with a way simpler one. 2, 4, 6, 8, 10, 12, 14, dot, dot, dot. Okay, so you can probably see the rule. We're counting up by 2 each time, right? And let's make a little table of values here that relates, greatest line I've ever drawn, the term number to the term value. Okay, term number to the term value. So term 1, 2, 3, 4, 5, 6, 7, and so on. So term 1 has a value of 2. Term 2 has a value of 4. Term 3 has a value of 6. Term 4 has a value of 8. 5 has a value of 10, right? Term 6 has a value of 12, and term 7 has a value of 14. We could write this equally as t1 equals 2, t2 equals 4, t3 equals 6, t4 equals 8, t5 equals 10, t6 equals 12, and t7 equals 14. Okay, same way you can do these. These mean the same thing. So essentially, these are 3 ways. 1, 2, and 3. 3 different ways to represent the same sequence. Okay, as the actual sequence, as a table of values, okay, or as just a list of terms that we know. Okay. Okay, so there we go. We have this now. And now let's just take a look quickly. How do we get these numbers, right? So we know the recursive, I mentioned before, recursive formula, right? Let me just actually copy and paste the table down here, right? That you add 2, right? You add 2 each time, right? To go between the terms, right? But what if I asked you what's term, I don't know, 100? Well, you'd have to figure out term 8, you'd have to figure out term 99 to figure out term 100. And to figure out term 99, you'd have to figure out term 98. And all the way back down to 7. So you're going to have to actually find all the terms in between. Unless, and that's true with the recursive formula. So this is called the again, we're going to talk about recursive formulas next section. Okay, but this time we're more interested in what's called an explicit formula. Okay? And that's a formula to say, if I just give you the term number, you can tell me the term value without having to know what's the term before it, or 10 before it or whatever, right? So, for example, this is an explicit formula. Right? Because you can tell me the value of the term if I just give you the term number, right? If I give you term 10, you would do 2 to the power of 10 plus 3 times 10, and that would be the value of term 10. So that's an explicit formula, because I can just give you any term number and you can tell me what the value of the term is. With a recursive formula, that's not true. You can tell me what the value of the term is as long as you know what the last term was, right? You can tell me what term 8 is because you know what term 7 is. But you can't tell me what term 100 is without finding all those steps in between. So we got to find the explicit formula for these values, okay? For this particular sequence. So the way we're going to do that is to notice a little bit of you got to notice a pattern here, right? So 2 is 1 times 2, right? Okay. 4 is 2 times 2. Okay, still pretty simple, right? Just draw all these equal signs. Do this, right? 6 is 3 times 2. 8 is 4 times 2. 10 is 5 times 2. And so this is where your pattern recognition skills are really important, right? This is why we study that a lot in school, is because sequences, you got to be able to recognize patterns to be able to solve them, to be able to figure out an explicit formula. So now if I asked you, okay, now bear with me here for a second, right? So the point I'm getting at here is that the term number times 2 is the term value, right? So let me write that out here, right? So value of the term equals, okay, 2 times the term number. You see that that's true, hopefully, right? This is, right, the value of the term is equal to 2 times the term number. And so now that we see that this is true, let's figure out a notation to help us out here. Okay, first of all, the first thing to note is, what if I just continued this a little bit and I put an n in, okay? N represents any whole number. What would I get out? Well, the pattern doesn't change. You know, if I put in 7, I get 2 times 7. If I put in 4, I get 2 times 4. If I put in 1, I get 2 times 1. So if I put in n, I get 2 times n. 2 times n. That didn't change. And so that is the value of term n. And so now this is how we write it. Value of term, okay, we really mean value of the nth term. Okay, which term? The first term, second term, third term? No, the nth term. N is just some number, okay? No particular number, just some number. The value of that term equal to 2 times n. And that is our explicit formula. This is an explicit formula, okay, for the sequence, right? Tn, right? Okay, what that represents term, the value of term n, where n is just some number. It could be 1, could be 2, could be 3, could be 4, could be a million, could be 101, right? Doesn't matter. It couldn't be a half because it doesn't make sense to ask for term half, right? When we're counting terms in a sequence, like right now, at least it just doesn't make sense to ask for what's the half term there, because you don't count like that, right? And it technically could be negative, right? So if this is term 1, I could ask what term 0 is, which would be the term before it. I could ask what term -1 is, which would be true terms before it. I mean, we can do that, but it has to be whole numbers, right? It has to be whole numbers here. And so that is our explicit formula, that Tn, term number n, is equal to 2 times n. So now I can finally tell you, well, okay, well, what's term 100? Oh, term 100, easy. I know what the nth term is now. So term 100 is just gonna be 2 times 100. Just 200. I didn't have to figure out term 99 or term 98 or all the way back to term 7. No. Right? With an explicit formula, I can figure out what term n is just by knowing the term number. Okay. Now, the biggest breakthrough of this lesson is that that's really a function. This is secretly a function, right? Think about it. It's a machine that takes in the term number, right? And it outputs the value of the term, right? In other words, f of n equals Tn. Okay? N, we usually do f of x. And when you say f of x, you're really saying any x value across the whole x line. Now, the x line is like the real line, so it has all the real numbers, every decimal number, every fraction. But when I say n, I particularly mean the natural numbers, or I mean even integers are fine, but whole numbers is what I mean. And so when I say f of n, I mean I'm only taking in whole numbers here. Okay? And so it's really a function, right? It's a machine, right? Let's go back to our lesson number 2, right? It's a machine, f, that takes in the term number and outputs the term value. For our particular example, f of n equals 2n. And you can see it's a function. So really, whenever I write t of n, that is f of n. That is a function, right? It's just a different way to write it. It's just a different way. And before you learn about functions, it's always written like that. But it is a function. It always has been a function. It's just that you never really called it that. And so that is the main point of this lesson here, is to notice that sequences are just functions, right? So sequences, write that here, are just functions which have a domain of only the whole numbers and a range of any real number. Now, I kind of didn't do all the examples, so let me just show you. The output of a function can be a real number. So for example, we can have a sequence 2, 2.25, 1.75, 1.25, 0.75, ... right? So the value of the term, right, doesn't have to be a whole number. But that is term 1, term 2, term 3, term 4, right? It's not term 3.5. The term number has to be a whole number. Okay, so that means the domain of our function that defines the sequence. Say that again. The domain, the function that defines the sequence is only whole numbers. Okay, and the output is any real number. It can be a real number. Okay, it can also be negative, right? So for example, if I have this sequence 6, 2, -2, -6, -10, dot dot dot, right? So we're going down by 4 each time here, and that's fine. We go into the negative numbers, totally fine, right? The output's real, but the input, the domain, is only whole numbers. That's term 1, term 2, term 3, term 4, term 5. Okay, so yeah, there is the main takeaway from that, which is just essentially this equation, right? That the nth term of a sequence is a function of the nth term. It's a function of the term number. Okay. Now let's take a second to define what a discrete function is. Absolutely, properly, right? So a discrete function okay, is a function which has a domain of only whole numbers. That's it. That's what a discrete function is. Okay. We say discrete because discrete means you just take it's a type of measurement. So for example, the number of cars in a parking lot is a discrete measurement because there can only be a whole number, right? If you go to every parking lot in the world and you measure how many cars are in that parking lot, you're never ever going to have 2.5, right? I mean, obviously if someone cuts a car in half, whatever, but that's not a real car anymore. So just counting, no different kind of examples like that, you're always going to have just a whole number of cars in the parking lots, right? But that's not true about everything. Like if you go into, I don't know, every, bucket of water in the world, that was the first example I could think of, and you measure the volume of water in there, it's never, you're not always going to have like 1 liter, 2 liters, 3 liters. You're totally going to find like 2.5 liters, 2 point, any kind of decimal, right? And so that would be called a continuous measurement. But a discrete measurement is where it can only be those whole numbers. And so a discrete function, we use the word discrete here to still mean only whole numbers. The domain of that kind of function is only whole numbers. Okay? Because it does not make sense to ask something like, what is the 1 and a half term? Term. We just don't ask that in sequences because there is no 1.5 term, right? So the function that defines a sequence is discrete. Okay. So I will mention here quickly. So the domain of a function which defines a sequence, okay, is it's a set notation, right? So it's n is our input, can be any natural number. Okay, any natural number. So let's just say for now we're only dealing with natural numbers, and so the symbol for that is that. Okay, it looks like this. So that, I don't think I can draw it as pretty a second time, is the set of 1, 2, 3, dot dot dot. Okay, of all these numbers. Okay, yeah, there we go. That is the set of natural numbers. Okay, and so we'll talk about adding 0 and negative numbers there another time, but it kind of goes as you'd expect. This is the real definition, though, right? So we have just natural numbers. And then the range, right? The range of f of n, well, that could be any, right? So f of n, or I'll call it Tn, right? So the actual value of term n could be any real number. That's it. Okay. And that's the whole thing. Now, it's down to specifics after this of the particular sequence, right? So, for example, this sequence has a range of, it could be any real number, but it's not actually any real number, right? Because you're never going to get like -5 out of this, right? So if you want to be more specific, although I doubt something you're going to be asked to do this in grade 11, but like you could specify the range here, right? Our range is, if I just say it, out loud in a sentence, right? The range is, what would we say? Okay, so multiples of 4, right? Multiples of 4 going down from 6. That's what the range is, right? So is some number a multiple of 4 going down from 6? Like 2? 2 is 4, 6 minus 4, right? Go down 1 multiple of 4. -2 is you go down 2 multiples of 4. -6 you go down 3, right? So -5 or 5 is not a multiple of 4 going down from 6. And so that's totally fine. That is the range. Okay, let's go through a couple examples here and try to see how it will go. So, okay, so the first question is if Tn equals 3n plus 2, okay, what are the first few terms? Okay, probably blocked by my camera there a little bit, but yeah. Okay, so to figure this out, well, we'll start at term 1, right? So it's going to be T1 is equal to 3 times 1 plus 2, right? Because Tn is 3 times n plus 2, so T1 is going to be 3 times 1 plus 2, just like a function, right? Exactly like a function, right? So we can just take this second here and show that Tn is just the same as f of n, just 3n plus 2. And so T1 is the same as just saying f of 1, something you're familiar with, right? Doing f of 1. It would just be 3 times 1 plus 2, right? Okay, so T1 is equal to 3 times 1 plus 2 is 5. Okay, and exact same thing for T2. T2, same thing as f of 2, would be 3 times 2 plus 2, which is going to be 8. T3 is f of 3, the same thing as 3 times 3 plus 2, which is 11. And T4, same thing as f of 4, would be 3 times 4 plus 2, which would be 14, right? Okay, and so now I can write our sequence. Well, it starts at 5, 8, 11, 14, ... It just asks for the first couple, the question, right? So there we go. That is our answer to the question. There's the first couple. I did 4. If it doesn't specify, just do like 3 or 4. Okay, there's that. Let's do the same thing here. What about, same question, but this time it's Sn equals 2 to the n plus 3. 2 to the n plus 3. And so, your term, essentially, the sequence, I mean, is labeled whatever this is labeled here. So this is the sequence T, and this is just another sequence called S. But it works the same, right? So S1, actually, I'll just quickly note here, this is just f of n, right? So S1 would be the same thing as f of 1, be 2 to the 1 plus 3, 2 to the 4, right, which is 16. S2 would be f of 2, 2 to the 2 plus 3, be 2 to the 5, 32. S3, f of 3, 2 to the 3 plus 3, 2 to the 6 is 64, and so on and so forth. So the sequence would be 16, 32, 64, and so on. Right? Okay. Let's take a moment here and actually graph these sequences. So you are able to graph sequences. Okay. They're a little bit, remove that. That's not the sequence. So this is essentially how you would do it. If you want to take a look here, if you're interested in doing it on Desmos, and this is essentially how you do it, you'd make this, which is just a list of numbers. I labeled it A from 1 to 30. And then I got to define some function, and then I want to graph all the points for these values here. So just copy this if you want to graph a sequence. And so I can just say f of n. Well, our example was 3n plus 2. Oops, not 3n2, 3n plus 2. There we go. And so there is our sequence, the first 30 terms of our sequence. So term 1, which has an x value of 1, right? So still the x-axis, but you can think of it as the n-axis. So we have 1 here, first value is 5. Okay? 2, 8. Right? And we can keep going up from there. So the 30th term, right here, 30th term is 92, right, in the sequence. And that's that first sequence we dealt with here. And now this one will be, it was 2 to the n plus 3, and it looks about like this. So the first 30 terms now goes up really high, really fast. And I want you to notice something quickly here. Let me go back to the other one. 3n plus 2 looks like this, right? The line y equals 3x plus 2 goes through all that, right? The line y equals 3x plus 2. Now you see our function was f of n equals 3n plus 2. So y equals 3x plus 2. Or you can think of it as a function f of x, or not, okay, I have to call it a different one. So g of x equals 3x plus 2. We'll go through all the points. You can think of like a function on the x-axis is just like a sequence, but you're essentially asking what is the sequence at all of these middle points here, right? Which is something we don't really do in discrete functions. So it's not a discrete function, it's a continuous function. But we have the same idea, it's going through. But just as a sequence, it looks like that, right? So the continuous function looks like that, 3x plus 2. The discrete function, 3n plus 2, looks like that for the first 30 terms. You can make that 300, and then we have all the way up here, right? And it goes like that. Okay. And then very, very similar, I'm going to make that back to 30, but very similar for 2 to the n plus 3, right? If I graph 2 to the x plus 3, but the plus 3 has to be in there. Make it, brackets, plus 3. There you go. And plus 3 has to be there. You can see that our exponential function also matches all the points, right? The continuous exponential function matches all the points. But as a sequence, right, we're only interested at the whole numbers, right? The x values have whole numbers. 1, 2, 3, 4. So 1. See, the x value is 1, 2, 3, 4. And then you can just keep going up, right? So this particular one goes up very fast. So the 11th term is already 16,000 and something, right? But there we have, right? So let's see here. This term, the 2 times 10 to the, the 20th term. I don't know why they write it like that. Sorry. The 20th term is already 8 with 6 zeros. So 8 million and something. Right? So obviously exponential functions go up very high, and exponential sequences also go up very fast, right? Just the same. So we have this here, back there like that. Everything you know about exponential functions applies to exponential sequences. It's just that you cannot ask like f of 2.5, because the sequence we're talking about now, not a continuous function, it's a discrete function. Okay, I got 2 more examples for us, and then we will finish off that lesson. So the next example is find an explicit formula for this sequence. So I'm going to say find an explicit formula for the following sequence. So let's take a look. I have -2, -4, -6, -8, -10. Okay. So how I would go about doing this is making a table of, and continues forever. So if I didn't say continues forever, then this is just a list. It's not a sequence. It's just a list of numbers. But if I say continue forever, now it's a sequence. That's why it is technically important to say ... at the end. We can make a table of values here. Okay, to relate term number. That's probably the best way to go about it. Term number to term value. Okay, so term 1, term 2, term 3, term 4, term 5, 5, -2, -4, -6, -8, -10. Okay, so we got to start trying to identify some sort of pattern here, right? That's the main point here. So the first thing to note, okay, well, we're going up by some amount here. Well, actually, we're going down. So we're going down by 2 each time here. Down by 2 each time. Okay. So that's interesting. That seems to give us a nice recursive formula. We already found so a recursive formula is usually pretty easy to find, depending on the situation, depending on what exactly is happening. But now the explicit formula, we have to sort of identify, okay, well, we're going down by 2 each time. So we start at -2. You can think of it like this. We start at -2. And then we have to count how many times we go down by negative 2, right? Go down by 2, right? So here, we've gone down by 2 one time, so we're at negative 2. So in this table, I want to identify the pattern, so I'm just going to copy and paste it here, right? And so notice that 1 times 2 is 2, 2 times 2 is 4, 3 times 2 is 6, 4 times 2 is 8, 5 times 2 is 10. Okay, that's an interesting connection we got there. But they're all negative. So what about if I say that this is equal to the term number times negative 2, right? Times negative 2. Okay, what about this one? This is the term number times negative 2. That is true. The term number times negative 2, right? The term number times negative 2. And once again, the term number times negative 2. Okay, so now if I say I just give you any random term n, and I ask you what is the value of that term, right? You'll probably tell me that it is the term number times negative 2. Or usually you're probably right, that is negative 2n. Negative 2 times the term number. Okay, great. So now that's our explicit formula. T of n equals negative 2n. So it's a lot of pattern recognition here. Try and identify a pattern that's going on, right? These can get pretty complicated, but I think the expectation is you should be able to identify the linear ones pretty well. Okay. These are linear because, if this was a function, f of x equals negative 2x, that would be a linear function, right? Because the highest power of x is 1, so the highest power of n is 1 here too. So you should be able to identify linear sequences. Okay, let's take a look at another one here, right? We have same question, but our new sequence is 7, 4, 1, negative 2, negative 5, negative 8. So once again, best to make a table of values that relates term number to term value. Okay. And so I'm going to say, well, term number 1 was 7. Term number 2 is 4. Term number 3 is 1. Term number 4 is negative 2. Term number 5 is negative 5. And term number 6 is negative 8. Okay, so now we have all these. And I'm going to show you a method to figure this out. So first of all, just check, is it going down by the same amount here? Is it going down by the same amount? So yeah, we're going down by 3, going down by 3, going down by 3, going down by 3, going down by 3. Okay, so we can identify this as a linear sequence. Why? Because we're going down by the same amount each time. Okay, so it's called the first difference. So the first differences are all equal. Right, the first differences are just, how much do you change each time? So we've gone down by 3, gone down by 3, gone down by 3, gone down by 3, gone down by 3. Okay. Since it's a linear sequence, this is exactly how we do it. The nth term will always be exactly this. Okay, the nth term will be, okay, so yeah, I'll just write it here. dn plus t0. Okay, now let me just specify here. So let me specify everything that's written here. The nth term of a linear sequence, okay, or I should say the value of the nth term of a linear sequence is equal to, okay, the common difference. Common difference is just this number. How much you're going down by in common. In common to all the terms. Negative 3, negative 3, negative 3. That's how much you're going down. Okay. Times n. Okay. N is you can just leave it as n. You don't need to put it there. Right. Like when you're finding y equals mx plus b. In fact, this is exactly the same thing as y equals mx plus b, but just with different symbols. We can, we don't have to figure out x's. You just figure out what m and b are, right? So same thing here. You just have to figure out what d and t0 are, right? And so t0 is, well, what if we went backwards one term to the 0th term, okay? So undo the rule. What would it be? If you're going down by 3 every time, going backwards by 1, you'd add 3. So it'd be a 10 there, right? That's the 0th term. Okay. And so finally, we know that this is tn equals negative 3n plus 10. Right, so let me just specify here. That is the 0th term. Now let's understand for a second why this is the formula, right? Why is this the formula? Because a linear sequence, right, is essentially, this is essentially saying, right? Let me try to translate this away. Okay, so this is, we start at 10, okay, and we subtract 3 n times. So try to understand that that's what we have, right? And maybe I'll write it in a different form so you can really see that. Tn equals 10 minus 3 times n. Okay, so if n was 2, that would be the same thing as minus 3 minus 3, right? Because it would be minus 3 times 2, right? So we can think of it like that. We start at some point, the 0th term, we start somewhere. The first term, we subtract 3 once. That's how we get to the first term. The second term, we subtract 3 twice, right? Subtract 3, subtract 3. Right? The third term, we subtract 3 times. So that's literally what we're saying here, right? To get to the nth term, start at your initial value, okay? And then subtract 3 n times. Right? And so that's always going to be true for a linear sequence, okay? This thing right here, I'll just highlight it in a box so you can write it down, right? This is an important one. So the value of the nth term of a linear sequence, how do you know it's linear? Because the first differences are all common, they're all the same, is going to be your 0th term, or start with your common difference times n plus the 0th term. This is exactly like finding y equals m. Let me write it with a better pen there. Y equals mx plus b. Because our y value is the value of our term, right? M, just like before, is our common difference, right? Even when you were finding m in y equals mx plus b in grade 9, grade 10, right, for these values, you would do this. You would find the common difference here, right? And so same thing here. Okay, times, instead of our input value being an x, now our input value is an n. And t0, b was our y-intercept, right? That was our y-intercept. It's where the line crossed through the y-axis. Now, it's just t0, which is essentially still where the sequence would cross through the y-axis. So that's why there's such similarity here, because they're really the same thing. In fact, I think understanding a sequence like this might help you understand y equals mx plus b a little bit better. Okay, let's take a second and graph these two sequences, and then we will be done. So Tn equals -2 to the n. Let's put that here. Or not -2 to the n, -2n. Oops, n. So we have that sequence. It goes down. Great. And then 10 minus 3n looks like that. So it also goes down because we're subtracting each time. We start at 10 here. In fact, I'm going to start at 0. So you see the 0th term is 10. And then our first term is 7. We go down by 3, down by 3, down by 3, down by 3. So we go down by a constant amount, so it makes a line. Okay, so there we go. That is our first lesson on discrete functions. It talks about sequences. Well, let's do a little review here, right? So we start with reviewing what a sequence is. Okay, we talked about the notation. Okay, how there can be rules to sequences. Okay. We talked about explicit and implicit formulas. Explicit and recursive formulas. And implicit formulas, something slightly different. And then we talked about how it is a discrete function. We talked a little bit about discrete functions. And then we did some examples of finding explicit formulas. Next lesson, we're going to talk about how do you find a recursive formula and how do you actually write it down. That's an important thing, because it's really easy to say, okay, start at 10 and then go down by 3 every time, right? But there's definitely has to be a better way to write that down instead of just writing the sentence, right? There is a way to notate that in math, and we're going to talk about it in the next lesson. Okay, so we're going to talk more about recursive formulas. So this was our lesson essentially on explicit formulas, because we were talking about the functions. And so next lesson is called recursive behavior. Okay, so if you have any questions, of course, you can email me at secondteacherprogram@gmail.com, or you can, of course, book a session with me or another instructor by going to the information information page for this website and booking a session. And yeah, that's everything for today. Check out the practice problems for this lesson, and I hope you enjoyed. I hope it was helpful, and have a great day. Thank you for watching the video. Remember, if you want me to teach you the entire course, visit my website, tutor.ca, and enroll in the second teacher program, which includes video lessons, private tutoring, notes, and practice problems for every section in grade 11 functions. Have a nice day.